Hi guys, James Earl here today with CSBreakdown. We're going to be going over the dynamic programming solution for the maximum contiguous array problem. So in this problem, we're considering a single one-dimensional array that can have both positive and negative numbers, and we're trying to find the range that has the largest sum. So let's dive in. So when we're considering the maximum contiguous subsequence problem, we're trying to find the largest sequence of numbers in this array that will find the highest sum. So, of course, your intuition is going to tell you that you would just take all of the positive values, but that's actually not always true, and we're going to see why. But first, we're going to consider the boundary conditions. So if A is an entirely positive array, the entire set will be the largest sum. As well, if A is entirely negative, you just take the maximum value. So if you had -6, -5, all the way down to -1, then you would simply take -1, and that subsequence is just a set with one value. So there's probably a few approaches you could take to conquer this problem, and a lot of people would consider brute force, but that's actually going to give you an okay time. A lot of the time when we're considering dynamic programming, the brute force option tends to be exponential, but in this case it's actually polynomial, and it's going to be big O n cubed. However, it is possible to make that even better using dynamic programming. So, of course, for dynamic programming, we need to consider a proof of optimal substructure. But trivially, the substructure is going to exist because you can actually consider some subsequence in the array from I to j, and if adding the j plus 1th value is greater than the optimal so far, then it's going to be included in that optimal solution for that subproblem. So the reason this is kind of trivial is because of the nature of contiguous arrays. So if it's going to be related to its previous values to form the largest sum, of course there's going to be a substructure property. So considering this relationship, we can define any subproblem to its previous subproblems given whichever yields a higher sum for that sequence, including the ith value or not including it. So we're going to define each index as it relates to the previous. Now let's say S at I is going to define the max sum over all continuous subsequences ending at I. We're then going to be able to define our recurrence as what follows. So there's two conditions in our recurrence. The first being that the very first value for S at I is going to be the first value in the array. So that's just your boundary condition. And the following condition is actually going to be the maximization. So comparing the previous, which is S at I minus 1, plus the next value in the array, or just that value in the array. So if we were to take the previous, so the S at I minus 1 plus A at I, that's going to be the same as appending the A at I value to our current sequence. But if we were to take the right-hand side of the maximization statement, the A at I, it's actually going to be considered starting a new sequence. So we can apply this to the previous example, and we're going to just build a short table and take a look at what we find. So of course we're going to consider the base case for when I is equal to 0. Of course it's going to be equal to the first value. Now the next is going to compare the previous statement, so S at I minus 1 is equal to -6, plus A at I, which is 2, is going to give us a value of -4, or the value of 2. So of course 2 is going to be greater than -4, so we take the right-hand side of the maximization statement and we place a 2 at S of 1. Now we're highlighting in red to note when we take the right side of the maximization statement, because this represents the start of a new subsequence, and we're actually going to be able to use this property later to find the maximum sequence. So we can consider the same process that we just followed. We're going to look at S at I minus 1, which is going to be the value of 2, plus A at I, which is -4, which gives us a total of -2, or the value -4. So of course -2 is bigger than -4, so we're going to append it to that list. Then we're going to continue this process, and we're going to see that the value of 1 is greater than the difference between the previous values, so we take it and we start a new list. And again, we're going to highlight it in red because this is going to be the next subsequence. We're no longer considering anything starting or any of the previous values. So now we're going to look at value 3, and of course because both are positive, we're going to take the first condition. So now we have 1 plus 3 is going to give us 4. Now -1 plus the previous is going to give us 3, but that's still bigger than -1. So this is why it's actually possible to include negative numbers in your optimal solution. So we're actually going to include -1 in this sequence so far. Now the next value is positive, so it's going to give us a value of 8, and of course that's going to be larger than anything we've seen so far. And the final value in the array is -1, but adding it in is going to give us a value of 7, which is of course greater than -1. So we add it in. But the trick to this is that it would imply the sequence goes from 1 to 7, or the 7th value, the array at the 7th index. But it actually doesn't quite work like that. So starting at the maximum value, we can move left until we encounter a number we've highlighted as red, and that's actually going to be what represents our optimal sequence. Because now we can see that 1, 3, -1, and 5 are going to represent the maximum sum of any subsequence given this array. And our value is 8. So now that we've done this, we're actually done. And we can see that we've created a big O of n solution, which is much better than big O of n cubed, even though big O of n cubed is still polynomial. So this is just another example of how great dynamic programming can be when it comes to certain solutions, even some that are a little bit simpler like this problem was. So I hope this video was helpful. Please be sure to like and favorite and check out our other videos on CSBreakdown. Thanks.